go ahead. And yes, let's continue where we left. So Chucky explained something very useful that maybe I'm going to share with you, and then if you like do it more in the discussion section. So we recall that we're in the context of some total space of, so we have some Farm variety Y, we're looking at its total space, and then we have its mirror, which has a description like this. So the description I have here is in the case where we're starting with the Pezzo surfaces. The Pezzo surface, where for this U, we blew up the base locus of some elliptic vibration, so then this U is really an elliptic vibration. There's a correspondence between left-shed spindles here, where you choose a point, you trace a path from like a singular fiber to a smooth fiber, that gives you a left-shed spindle, and then using double suspension, you could lift this to a compact Lagrangian inside Z. Now, this fits into a more general framework, which is if you have so you have a map from KY to C. This F would be in what I did earlier. This would correspond to a section of H0 of minus KY on Y, and if you choose F to be general, then we want to choose F to be general. And then remember this map here is a smoothing of in the central fiber you have Y, and then you glue to it along the divisor, you glue to it the total space of the line bundle, which is O of minus D restricted to D. Okay. This. So you have these two components, and this map is a smoothing of this. Now, if we remove some generic fiber D of this map, then and if we shift the map by 1, yeah, and we move the origin, now we have we remove this fiber, and everything else is a smoothing of this, except for the singular fiber. Okay, that's the geometry. Now, this corresponds to just a regular fiber, which a regular fiber of this will really exactly be P2D, would exactly be or Y2D. And then this will so this is the A side. On the B side, we will have that this corresponds to the Z that I wrote down here. Now the Z does admit an S1 action by replicating the conic vibration. If you take the symplectic portion of this, you will get UU. And then the prediction of many people, or of mirror symmetry, is that these two have equivalent homological information, whether you're looking at DB core or Fourier type categories, these as well, and then mirror symmetry takes you from one to the other. And I think so maybe there will be some talks about this next week, or discussions. Yeah, fantastic. All right, now so this correspondence is also at the level of comorbidity invariance, and so yeah, anyways, there's a lot that can be said about this. I can, if you want, I can give you a sketch of why the comorbidity invariance of this and this should be the same, or I cannot. It depends on you. This way, okay, fantastic, thank you. Right. So relate. So GW genus 0 of ky corresponds to GW log of genus 0 yd. So this is a statement that has a long history. So this started by work of Takahashi. This is Nobuyoshi Takahashi, Gartman, Andreas Gartman. This was really yes, indeed. Gartman, so this is around 2000. It's really long time ago. This was before we had a definition of relative comorbidity invariance. Then we had 2 decades of defining relative comorbidity invariance and non-comorbidity invariance. And then there was a paper we had with Graeber and Bullard, where we proved this in fairly large generality, and this was at the level of logic fundamental classes. This was taken up in work by Rousseau, Pierre Rousseau, Hongwu Fan, Shui-Wen Guo, and Long-Tin Wu. So I did mention this before. And then there's also all types of invariance correspondence that was done by Fei Long Yu and Yu Wang. So I also mentioned this at the end of this. But let me just tell you the kind of original story, which goes as follows. So this one is also high genus, I should say. High genus, and then this one is, so here is just maximum competency, and then this one is all dimensions. So this one is just dimension 2. This one is all dimension. This one, there's a statement for all dimensions, but then the statement for all dimensions is fairly complicated. The statement for dimension 2 is much simpler. This one is all dimensions, which is only genus 0. Okay, so you start with the degeneration to the normal cone. We take the product of y times a1, and then so you blow up d times 0 in the product of this product. So what does this look like? So we have also central fiber. So with the general fiber, this is 0. With the general fiber, you have y. And then with the central fiber, you get y union, y union along d to some projective bundle, which is projectivization of the normal bundle O minus d plus O on d. That's just yeah. This is just. Did I maybe?
Sure.
Maybe I need or should I?
It's okay.
Yeah.
It's the same.
It is the same. Yeah. But you're right. Well, so in any case, I want to wait. So this direction, I have the normal bundle in this direction is O minus d. I think. Normal here OD and then O minus d. And then here we're going to have O d. Okay, so this is not enough because this is just degeneration of y. So what we want to do in addition is we want to degenerate. So you want to look at this d hat, which is this is the strip transform of d times a1. And then we want to look at L, which is the total space of O minus D tilde. And then what this does is this this adds a line bundle everywhere. So then we have this nice picture where over, so this is 0, over the central fiber, we will have O minus D. Over 0, we have, so this is Y times A1, and then along E, we'll have some other line bundle on some line bundle L. So L, this one is L, which we could just call this. So the name, let's call it X. And so here you can see that, and then you know, then we apply the degeneration formula. We apply the degeneration formula. And this gives us a statement that relates the Morgan invariance of O minus E relates then with the Morgan invariance Y comma D and Morgan invariance of. So when I write it this way, of course, this is a line bundle on a projective bundle on E, but there is in the but there are various simplifications that occur that allow you to state it this way, and so various simplifications. So various simplifications, and then the statement becomes that the Morgan of ky is equal, so this is G0, any class is going to be minus 1 to the d times beta, so here I have G0 and class beta. D times beta minus 1, D times beta times the Morgan invariance of the maximal tangency Morgan invariance of also G0 beta of Y. But what is, let me explain to you what this is. So maybe a good way to write it, well, so the log invariance, we don't need any such assumption. The only thing we need for the general statement is that D is net. Yeah. However, so this statement works if D is net, and then sorry, here I could just take O minus D. Yes, yeah, okay, I see the point. Good point. I could just take O minus D. Yeah. And then this works quite generally. There's also extensions, by the way. So there's also like a lot of extensions to several components. So this is work by Fegnon and H.H. Where D has some components. So here, yeah, so the log, so maybe these are, we just write maximum tangency per second. So these are the log written of maximum tangency. They count curves like this. So we have Y, we have D, and then you're counting curves that meet the divisor in only one curve. So only in one curve. And of tangency, D times that curve. So in general, you would meet it in D, in C, in D times beta points, and then you're moving them together.
So you say 1.1.
That's right. Good point. That's right. Because yeah. Just trying it. Drawing it. Absolutely. So the way, so yeah, you have some moduli space of log curves where you're mapping this. You have some like some stable log map, and then you're mapping it to the divisor. And then it is true at this point that it's going to do map like this. It is true that so this point has to map here, but some components could map into the divisor. So there's a lot of you can have various like stuff mapping into the divisor, but there could also be some like several components. But it's quite a messy story. So and then when I say, maybe you want to think about y times a1, comma d times a1, right? Because that's the geometry we have. And then if you do this, then it'd be clear that in higher genus, we will get some lambda classes. We'll get -1 to g lambda g, where lambda g is the top-term class. Anyway, this is this work by Curie, Schreck, yeah, so there you go. Maybe I can say a little bit about the proof of Gartman, because that will be a segue into the next part about eye functions. So, following popular requests, I'm going to talk about eye functions. But, yeah. I will say maybe one more thing first, which is that if we take this thing and we apply IMS, so apply IMS, we get a family which is UV equals 1 plus 1 minus 2 t plus 5 square minus 3 plus x plus y plus t over xy. And then let's call this 1 plus ds. And then there's some work by so Tran and now Lim now Sen and Lao. This is a generating function. And so what we're counting here is sorry here I can't do this is for P2. Yeah, I think y. And then here this is y. We have some Lagrangian. L, some Lagrangian, and we're counting curves like this. So there's a component which is this degree d component, which is going to be the degree as measured by this, and then we're counting open invariance and Lagrangian with this half of the fiberglass. And the reason I'm mentioning is these are the quantum corrections that lead to canonical coordinates, lead to canonical coordinates. And so when I finally get to do IMS, we should be really viewing these canonical coordinates. And then also in their paper, they show that so the MC and MK, the ones we talk about so much, are identified via this MK check. So this is here I put KP2. No, the other way around. Here I put Z, and here I put KP2. Yeah, I'm just doing it in this example. So you do, yeah, so this is point and I'm just doing the case Q2. And then the identification is that we need to replace Q by Q to the we need to put T here and then T to the down 1/3, 1 plus G T. Is this or do I have minus 1/3 here maybe or 1/3 here? Something like this. I wrote it up. I was too confident that I was doing it. Minus. Oh. And now the other way around, if you do the other way around, then we replace t by t to the exponential of the sum of minus 1 to the k 3k to the k. Why am I writing this? So now, trick question. Have you seen this before? Have you seen this before? Anyone? This week, not in the past. That's right. We saw this in a different context. In the context of periods of ellipticals. So we'll get back to this hopefully on Sunday. So it's not an accident that we have this here. So I want to, or maybe we might be able to say something about this today. So one part of kind of my interest has been to make sense of these, geometry. So explain the gems of this, right? What's the geometry of these statements? Right? So that's something I want to get. It's not accidental we have this precise shape. There's some geometry behind that I want to get. All right. More questions? Comments? So now I give you the final punch, because we're going to talk about J functions. If you feel extremely unhappy, I will point to you the people you should blame. So I should say so now I should actually. So here we really say y is final, d is smooth and canonical, and now the goal is really to understand. So the goal. So we have genus 0 from a written theory of y. So let's say it's always genus 0, so always genus 0. Then you just stop using the word. So we have the Gromov-Witten theory of y. We have the Gromov-Witten theory of ky. We have the Gromov-Witten theory of y comma b. GWS, GWY. And we have GW. So the goal. So the goal is what? To find all arrows between them. So it's kind of, the goal is to have some unified framework. When I say all arrows, so these two we know are equivalent by log local. And here, sorry, I'm also, when I take this, I only take maximum tangents. Yeah. So now the goal is to like find errors between all of them. So first of all, because these are equivalent by log local, I'm just going to start talking about this one. Just makes my life a bit easier. Because this one involves a lot of signs. Signs are, as you can see, there was some signs. Now, I want to understand what are these errors and what are these errors. And the errors are always going to be of the form. The invariants are equivalent if you add this extra information. And this extra information is always going to have some geometric interpretation on the mirror side. So every arrow is going to be, every arrow is equivalence after adding a sequence of invariants. And so that's goal number one. Goal number two is describe the mirror geometry. So the mirror relationship via periods. So I don't want to, really don't want to, I don't want to, I want to have some like very nice geometric explanation on the mirror side. And then when I say GW, I really mean J function. So which is a subset of the Enumerative theory. And maybe the goal 3 is get rid of mirror maps. That's a goal 3. And you know, when I say get rid of mirror maps, that really, it's only then we see the geometry equivalences. Let me make a statement. Let me tell you what the statements are. So what's the geometry of log local? Can someone tell me? What's the geometry of log local? So B side log local. So the B side log local should be integral over Lefschetz Finkel is the same as the integral of the suspension. Some other class. Okay, these are the equations. Yeah, that's which is remember this correspondence we're talking. If you have some Lagrangian, you can lift it. It doesn't even have to be Lagrangian. Just if if you have some left shift symbol, you can move to 2 less 3. We described this yesterday. And then it's just a statement that these integrals are the same, and so this is also quite classical. I learned about this in CLT, but I guess it's very classical. But that's kind of beautiful geometry. So then the B side of this one, so B side of can someone guess? So one of them should involve this, right? So what can the other side possibly be? What's that? That's right. Yeah. Integral over what?
One cycle.
Yeah. Which one cycle?
One cycle inside the boundary.
The boundary, exactly. The integral over the boundary. So this is kind of Stokes, right? So we still need to write here like so we need to write this as like d omega and omega something. Okay? So this is Stokes. Now, when I say this is actually a little bit misleading because this gets mirror maps make this statement very annoying. So this is. So the claim is after mirror map headaches. And I really want to remove these mirror map headaches. But also, when you do the correspondence between these two sides, there is also, as I said, there's always some extra information, and the extra information to go from here to here, you need to add a sequence, which is basically some sequence of invariants, which is given by quantum efficiency. So we have to add something. We have to add something which I'll explain. And then if you go from here to here, we also have to add something. And sometimes that something is a modulo 4. Sometimes. And it's kind of, when the mirror family is modular, this will be a modulo 4, which is going to be really tricky. On this side, to go here, you do a Fourier Laplace transform. To go back, you need to remember some information. You need to remember, so to go back, you need period integrals that D doesn't see. If I only integrate over these H1s, I don't see integrals over some SYZ fiber that are away from D. I don't see them. But if I add them back, I can go the other way around. Right. So this is kind of a vague explanation, but I want to get there. And I said, so this type of question has been studied before. Quantum efficiency is known, it's been known for a while. But everything becomes very kind of clean and it becomes very geometric once you apply IMS, so intrinsic reason, to the question. Right. Now in the next 50 minutes, I'm going to prove everything that's written there using J functions. And then on Sunday I will do it again on the B side using period integrals. So please bear with me. This not going to be tricky. So first I write out the J function of y. Here, y will be a canonical coordinate for little y. And so this, by the way, will also involve this story. Like, there's really an important part, which is, like, identify a relationship between the symplectic parameters. So what this means is I go into the symplectic literature, I look for something that looks right, and I declare this to be my symplectic invariant. We can talk about this. But here, so I always take C1 to make the statements. If I didn't take C1, the statements would not be as nice. So this is defined to be C1 divided by Z. So sorry, y to the C1 divided by Z. So this is the thing we've seen is at 1 plus log. So 1 plus C1 log y divided by Z plus C1 square log square y divided by Z 2Z square, etc. Product 1 plus, this is identity homology. So effective curve classes, I keep track of the dB, 2 greater than Z. This is an element, well, let me tell you what is G by the Z. It is the sum over some alpha, J, alpha beta, Z, which is the sum over alpha of T, J, alpha psi, sigma beta, plus N minus J minus 2. And this is a logarithmic invariant of Y, G in 0, 1 mark point plus beta, T, alpha J, Z, C1, beta plus N plus J, where T J alpha is a homology class in H to J. So could I mention J class in Q coefficients? T J alpha is a dual class. So dimension J, could I mention minus J? So they are dual classes dual. So like I said yesterday, they pair to 0 unless alpha equals alpha and J equals J. So J keeps track of the codimension or dimension, and alpha keeps track of it as an index. And then here, remember when I wrote down the J function, I was like summing over. There were some terms which were C1 to some power. So here I removed them outside, which I can do. And then here we have these homology classes or some psi classes, and then the dual pairings. N, big N is a dimension of Y, and then this is a class which is in homology Y, C. But I also have to invert Z. I have to take logs of Y, and then it's a power series in Y. Now, yesterday, well, last time I wrote down the J function, I just wrote the sum over, I didn't spend like, I just wrote down all the possible terms. Here I really chose everything so that that guarantees that I get classes in the correct virtual dimension. It's an ugly expression. I agree. Check. Any questions, comments? All right. So this is J function of y. Now, let's look at the J function of the pair. So for YD, I'm going to take my Kähler parameter to be C1 log T. So I'm not explaining you why that's a reasonable choice. And in fact, I should say that, so compared to so this relative J function was defined by Fenglong, Fan, and so Fan, Kongu Fan, HH7, and Fenglong U, and developed later in also some further works by subsets of them. So and compared to them, we push forward to the cohomology of Y. The reason we push forward to the cohomology of Y is we want to have this list of comparisons, which we couldn't do if we just, so they do it in a more complicated, the orbifold cohomology way. But we want to make these comparisons, and for this we need to push. So we define this. This is given by and I'm also modifying the definition slightly in order to get some more convenient statements. But my changes are inconsequential. So what are these? So when I write, this notation stands for G to 0, one point of maximal tangency, so that's why there's a parent physics with the divisor, so C1 times beta. The divisor here is C1, and curved class beta. Here, we can have some insertions that are pulled back from the divisor, which is why I write it this way. So we have insertions that are pulled back from the divisor, but we're only looking at insertions that come from outside. So we only look only insertions station. I think there's a name. Only insertions from Y. Of course, D could have more interesting cohomology, but we're only pulling back. We're only taking. We're only using insertions that came from psi class, just a usual psi class. And here we have this modification, which is because we're pulling back. We're looking at insertions that come from Y, and then we have to change this by C1 times this. So there's a bit of yoga to correctly push forward to Y, but this one should be. So this is about good question. So basically, so the way here we use some duality between these two. Now, when we're looking at relative invariants, so we have to the duality lives in the cohomology of D. So that's why. So if you look at their paper, they have a more refined statement where they take products of the cohomology of the divisor, and then that keeps track of the tangency. So this is really an example of these. So I'm just really, I'm kind of being very brutal and I'm pushing everything forward. And then this is a statement mechanism. Right? And then there's also a I function, a relative I function, so this is also in their work. So this is a twist. So if you look at the expression we had here, so you take this expression and then you multiply it with these twists here. These are some twists. So they, like for example, they also show up in, if you look at the proof of Lewis symmetry for the primitive by Michel and double L's. Jan and you, then this sort of thing also shows up. But actually, sorry, I should say that it's a different twist. Yeah, here we go from 0 to C beta minus 1, C1 plus NZ. Those are the twists. And then the mirror theorem. That's right. So now I use Y because I'm twisting the J function of Y. And now the mirror theorem will be that JYD is of C1 log T Z is going to be IYD of C1 log of YT Z for some YT. So YT is the mirror map or the inverse of the mirror map, right? Okay. Sorry, I'm fast running out of time. So so this is the mirror theorem by Fontaine. And in fact, sorry, even this YT we can explicitly say this is quite explicit, and it relates to the one I've shown you before, the start of the. Okay, thank you. Then I can say what this one is. And I can even use the notation I have in my notes, which is so this notation is entirely unjustified. And I apologize for it in advance. It's very dangerous what you just did. You gave me three. Okay, so let me try to be very efficient. So maybe I don't tell you right away what this YT is, but I might tell you in a bit later. So perhaps one thing I want to say then is that there's another twist for just the y function of d, and if I do the twist for the y function, the I function of t. I don't go from 0 to this, I go from 0 to C1 beta, yeah? From 1 to C1 beta, I have this shift, yeah? So this will give me the I function of D. And then you can check, like, you can check, I also want to multiply with C1, but I don't want to have the Z, yeah? And if you do this, if you define the function of d this way, then this will imply that y d by dy, I yd, c1 log yz is equal to I d c1 log y z. And this is the proof of quantum Lefschetz. So this is So I just proved this is proof of quantum motions. So if you ever thought quantum left shifts was hard, it's not. It's just that for one of the I functions we go from 0 to C beta minus 1. For the other one we twist from 1 to C1 beta. And then the way you can keep track of the twist is by this extremely simple relationship. And then that, if you just translate this to the J functions, you get quantum motions. I can say more about this next time, but at this point, I want to say something really cool about these twists, which, given the time I have left, let me just say something really cool about these twists, which goes back to Gartman. So Gartman, and it's actually so this goes back to Gartman, but it's also 25 years later generalized in a recent paper by Felix Yanda and Tony UAU or UAU. Sorry, I think it's correct. Yeah. So what they, for them, these twists here from m equals 0 to C1 beta minus 1. So this is a naive tangency. And this means that it's really a topological way of proposing tangency. So how does it work? What I mean by naive, I mean the following. Is you start with the organized space of maps, G is 0, 1, 1, plus beta, to Y. Okay. And then, so here we have just like good curves in Y that don't know anything about the divisor yet. And then we start to impose, we start to multiply, so we take the virtual fundamental class of this, and then we start to impose these conditions. So first we multiply by C1, and then we multiply by C1 plus psi. Actually, I should say, I should replace this by psi at this point because that's what this will be. Psi, and then I do C1 plus 2 psi, etc. And what this does is I have this point here, and then I require, in the first step, I require that this point should be on D. Yeah, that's just insertion. Yeah. At the second step, I require that we get this wrong. So jet. Okay, I didn't write this up nicely, so I'm going to get this wrong. But it's something about jet bundles. Someone can help me out. Which is saying that I want that this locally satisfies some tangency using the jet scheme. I didn't prepare that part, so I'm saying it incorrectly. And then you keep doing this, and if you do this all the way to this level, then you get these twists, but also then that invariant that you get here. So the generating function of these invariants by lambda is a generating function of invariance with naive tangency, where this naive tangency is described by using jet bundles. So this uses jet bundles and derived algebraic geometry. Okay. So I need to look up the precise statement. But if you wanted to topologically impose this tangency, you would use these jet bundles. This would be some Chern classes. This would be some Chern class. Maybe this would be Chern class of jet bundles. And then this process of multiplying with successive things corresponds to increasing the tangency at that point. And then what Garrel shows is that if you do this and you apply this at each step, your moduli space becomes, at each step you have C1 plus M psi times the previous moduli space, where you impose tangent C M minus 1. So, yes. Plus some corrections. Let me say it one more time. So in this process where we keep multiplying by these things, this increases the tangency at the point by 1 more, but there are some correction terms, which really we don't want to, I don't want to describe now. Does it make sense what I'm trying to say? So we have a moduli space. So after like m iterations, we have a like good moduli space where we have a certain tangency here. At the next iteration, we're increasing the tangency by 1, but there's a price to pay, which are some corrections. Yeah. And then the mirror map, what the mirror map does, it removes the corrections. So in other words, the theorem that is stated here by Franz and Yu is if you did not apply the mirror map, then this would be a generating function of Enumerative invariance with naive tangency. And applying the mirror map has the effect of getting, like, cancelling out all these corrections. And moreover, something that was already present in the work of Gartman, if you go beyond C beta minus 1, if you go, first of all, if you started with 1, and then you went all the way to C1 beta, sorry, if you went all the way to C1 beta, at the end everything is inside D, or 0. And using that principle, you can recover the invariance, the counts of curves inside D from this iterative process. So that's how it's very similar to Yao's proof, where you're looking at curves, Yao and looking at curves inside Y, and then you can want to require them to be inside the hyperspace, which this process does eventually. Right. Yeah. So let's take stock. I claimed that I was going to relate the J functions of Y, the J functions of Y comma D, and the J functions of D. Right now, I've showed you using, I give you some like hints how you can go from this one to this one. I didn't expect. I will review this next time. But basically, if you know this one, you can change your scalar parameter by something, and then you will get this one. Doing the inverse takes you the inverse way, and then we also have to like study what happens, how to relate them. So sorry, I run out of time. Well, maybe we'll get back to this, and then we'll finally. So we'll get back to this, and then we'll finally go on IMS. Hopefully, that's what I've been promising endlessly. Yeah. Okay. Yeah.